My dear students, today I am going to discuss about junction, PN junction diode. So in this PN junction diode, you can just see a p-type semiconductor in which holes are majority carriers, and there is an n-type semiconductor in which electrons which are in E shape, they are the majority carriers. Holes are minority carriers. Here electrons in blue color are minority carriers. So when p-type semiconductor and n-type semiconductor are suitably joined, you can just see here electron is represented with symbol E and hole is an empty space. So let us see how the depletion region is formed. You can take a p-type semiconductor and n-type semiconductor when they are suitably joined. What are the things happening? Let us see here now. First, some of the electrons will fall in the holes, and you can just see positive ions or negative ions are left. You can just see what is going to happen now. So electrons will shift in the holes, and here when electrons are donated you will get positive ions. When electrons are accepted you are getting negative ions here. Okay, and this region is called as depletion region. You can just see what is going to happen. So here you are going to see positive and negative charges which are called as immobile charge carriers. They don't have any mobility. They don't allow even further movement of electrons and holes also. They will stop. This is called as a depletion region. They are depleted. They are emptied with electrons and holes, positive and negative. This positive and negative, they are called as positive immobile charge carriers and negative immobile charge carriers. Now let us see what is going to happen here. So this region, there doesn't have any electrons and holes. That's why they are called as depletion region. Now let us see what is going to happen here. So this depletion region is acting like a potential barrier. Okay, it's acting like a potential barrier. Further movement of electrons and holes, they will block here. Now how this is working, let us see. So this is p-type. This is going to be n-type semiconductor. Now here near the positive charges you are seeing electrons. Near the negative charges you are seeing the holes. Understand? So let us see what is going to happen. As soon as you join here, electron will fall in the holes. Electron will fall in the holes here, isn't it? And only at the edges these electrons will fall in the holes, and here positive ions or negative ions are formed, and this is called as depletion region. This is called as a junction. Junction of two diodes. I mean positive and negative type. N type means negative type, P type means positive type. Okay, so this is a potential barrier. This potential barrier does not allow further movement of electrons and holes, because this electron trying to come this side, this positive charge will drag it backwards. Here, you know this is a p-type semiconductor, n-type semiconductor. In p-type semiconductor, p means positive type, n means negative type. In positive type, holes are present. In negative type, electrons are present. Here this is holes. Block diagram in which holes are majority carriers and black colored dots are minority carriers. In n region, negative region, here electrons are majority carriers and the holes are minority carriers. So this is a block diagram of p-type and n-type semiconductor when they are suitably joined. When they are suitably joined, what is going to happen? First of all, the electrons shift to the holes. The electrons fall into the holes and there is a depletion layer formed here. At the edges, if you observe, okay, at the edges, whatever the electrons are present here, okay, whatever the electrons are present here, the electrons present here, they will fall into the holes. The electrons present here, holes are present here. These electrons will fall into holes. That means here in this region there are no electrons, in this region there are no holes. That's why they are called as immobile charge carriers. This is called as depletion layer. Depleted with the charges. That means no protons and no electrons are present. Depletion means emptied. They are emptied from electrons and holes. These are called as immobile charge carriers. They don't have any mobility and they doesn't allow even any mobility also. For example, this hole is trying to cross the junction. You know this is going to be the PN junction. This hole trying to cross the junction. Okay, what is going to happen? Now let us see here. My dear students, near the positive charge electrons are present, near the negative charge holes are present. Now this electron will fall into the hole and there is no electrons in this region, no holes in this region, because already electrons will be shifted into the holes and holes will be closed. So no electrons and holes you are going to see in these regions here. So they are called as depletion regions. Depletion layer. Depleted means they are swept, cleaned with charge carriers. No charge carriers are present in this. So only positive ions are present here, negative ions are present here. So these positive ions, they are acting like a positive terminal of a battery. These negative ions are acting like a negative terminal of a battery. And hence it is called as a potential barrier or barrier potential. And here, this barrier potential does not allow the further movement of electrons and holes. What is the reason behind that? For example, this is having negative charges, means electrons are present here. Electrons, these are electrons, and these are holes. Okay, p-type semiconductor holes are majority carriers, electrons are minority carriers. N-type semiconductors, electrons are majority carriers and holes are minority carriers. Here electrons are present, electrons are majority carriers here now. So for example, this electron tries to cross the depletion layer, these positive charges will drag it. This will not allow to move, and this negative charge will push the electrons because electrons are negatively charged bodies. So this electron cannot cross the potential barrier. They cannot cross the depletion layer. Now, for example, these are holes here. This hole trying to cross the junction, these negative ions will drag the positive hole, will stop the positive hole, hold the positive hole here, and by chance the positive hole try to escape to the junction. This is junction. These positive ions will push the holes because holes are positive charged. Hence, there is no mobility, there is no further movement. That's why it is called as potential barrier. Barrier means itself just like a wall, does not allow further movement of electrons and holes. Hope you are understanding now. And because of which this is acting like a potential barrier. If you want the electrons to shift that side and holes to shift that side, electrons to shift this side, what happens? What should you do here? You have to apply the forward biasing. Forward biasing means what? This is a P region. P region means positive region, and N region means negative region. So when positive is connected to positive and negative is connected to negative, when anode is connected to positive and cathode is connected to negative region, so P positive to positive, negative to negative connections are there. This positive and negative will cancel the potential barrier. And further current flows. Why? Because this positive will push this positive and this negative. This positive, when they are connected to the battery and negative is connected here, this positive will push the holes, this negative will push the electrons, and further current starts flowing. This is called as a drift current. Understand? So current is drifted forcibly by the applied potential here. Applied battery supply. So then, if this is a potential barrier, to cancel the potential barrier, we need certain voltage is wasted to cancel the potential barrier. And it is different for silicon and germanium. You can just see the graph. As soon as you apply the forward voltage, current will not start flowing from here directly. Some amount of potential is wasted up to here. Up to here, no current flows, because applied voltage has to cancel the potential barrier, then only current starts flowing. When potential barrier is eliminated, then only current starts flowing. And potential barrier is eliminated at 0.3 volts for germanium, and for silicon diode it is eliminated at 0.7 voltage. So at this place the current starts increasing. Here at 0.3 volts the current starts increasing. So for silicon and diode, potential barrier voltage is different. Germanium is having a very less potential barrier. For germanium, it is easy to cancel the potential barrier. For silicon, it is very difficult to cancel the potential barrier. Hope you are understanding what I am going to explain. So once you understand this concept now, it is very easy for you to understand the problem. This is called as reverse bias. Reverse bias means positive connected to negative, negative connected to positive. This is called as reverse bias. Now ions will move and depletion layer size will increase. Depletion layer size will increase. There is no transfer of electrons and holes. No current flows. And hence, let us see what is going to happen. When a p-type semiconductor negative type, n-type negative means whole electrons here, holes are present here, positive charges. Holes are positive charges. Free electrons negative charge, free holes positive charge. So holes and electrons are present here. Let us see what is going to happen now. So this is called as PN junction, space charge region. These are called as immobile charge carriers after transfer. Okay. So this is called as forward bias. Forward bias means positive is connected to positive type and negative is connected to negative type. Then again further holes are pushed through. This positive will push the positive charges. This negative charge will push the negative electrons and further current starts moving in this case. Okay. So this is going to be forward bias. Forward bias means current flows. Reverse bias means no current flows. That is the meaning of this structure. Okay, my dear student, this is a previous year question of NEET which was asked in 2015. You can just see what is this happening here now. It is given that an external resistance is 100 ohms and this diode, okay, so this is having a potential barrier of 0 point. That means this diode is having a potential barrier VB is equal to 0.5 volts. Applied voltage is 3.5 volts. Okay, resistance is 100 ohms. He is asking us to find out the current here. How are you going to find out the current? You can find out the current because you all know I is equal to V by R according to Ohm's law. But applied voltage, here you are going to apply the voltage VA, whereas the potential barrier voltage is VB. So here you have to consider the voltage difference. Applied voltage minus barrier voltage, because the applied voltage has to cancel the barrier, potential barrier of the diode, then only the current flows. To cancel 0.5 volts is wasted. So that's the reason we have to write VA minus VB by R. So what is VA here? Applied voltage is 3.5. So to cancel the potential barrier 0.5 is wasted. So we have to remove that one, and resistance is going to be 100 ohms. So what are we going to get here now? 3 into 10 power minus 2. Okay. So this can be taken as 30 into 10 power minus 3 amperes, which can be taken as 30 milliamperes is going to be our answer. Thank you very much.